Hello everyone, thank you for joining us today for our Lead and Copper Control with Phosphates webinar. I am Liz Mueller, our Marketing Manager for Carus Corporation. A few housekeeping items before we get started today. We are recording today's webinar. We will have it available on demand after our live session. All attendees will receive a follow-up email with the webinar link to access the presentation. We encourage you to share this within your organization and network. If you are interested in receiving a PDF of today's presentation slides, please contact us and we will get you a copy of that. To ensure the best audio quality, we have everyone in listen-only mode. If you have questions, we encourage you please submit those throughout the presentation as you think of them in the question pane in the GoToWebinar panel. We should have time at the end for questions and answers. If there's any we don't get to, we will be able to see who asked a specific question. We'll follow up with you directly. Here are a look at our 2016 webinars that we had hosted previously in this year. These are recorded, and we do have those recordings available on our Carus Corporation website. If you would like those direct links, please visit us at www.caruscorporation.com. We should have our 2017 webinar series finalized in about the next couple weeks. We'll have that posted on our website. We will also be posting that on our social media platforms as well as sending out an email blast in early January. If you're currently not receiving those email blasts, please let us know and we will get you added to the list. And how to find us. So here is our website address as well as two email addresses, our general sales and marketing email address and mine. We are on social media. Please follow us. We have Facebook, LinkedIn, and Twitter accounts. We frequently will post technical articles, upcoming events we are attending, webinar schedules, and recordings of our webinars, and much more. And with that, at this time, I would like to take this opportunity to introduce our speaker, Mr. Darren Scott. Darren has worked for Carus Corporation for 16 years, with the last 2 years as a technical service manager. As the technical service manager, Darren conducts laboratory testing and product demonstrations for Carus Corporation's municipal, industrial, and environmental customers and prospective new customers. These product demonstrations include technical training, safety presentations, and installation of safe chemical handling and dosing systems. He's a graduate from Illinois Wesleyan University, Bloomington, Illinois, with a BS degree in chemistry, ACS certified. Mr. Scott is a member of AWWA, Water Environment Federation, and the American Chemical Society.
Good afternoon. So we're going to talk today on the agenda. First, we're going to talk about the US EPA lead and copper rule. Then we're going to specifically talk about factors that affect corrosion and prevention, a brief history of phosphates, how you would select a phosphate product, what the benefits are, some dosage rates for different phosphate products, case studies, and how you would go about monitoring corrosion control success in your distribution system. Currently, the rule that's in effect for the lead and copper rule is from June 7th of 1991. What it said at that time was action levels for both lead and copper in the distribution system at the customer's house. For lead, the action level is 0.015 milligrams per liter, or more commonly referred to as 15 parts per billion. The copper action level is 1.30 milligrams per liter out there in the distribution system. At the time of the rule in 1991, they set maximum contaminant level goals for both of those. For lead, they said the goal should be 0. With the current issues in Flint, Michigan at the beginning of this year, that has been brought up by many different people, saying that the goal should be 0 milligrams per liter versus what the action level of 15 parts per billion. The reason these rules were put into effect is the health effects that both of them can have on the consumer. In lead, the one we typically think of is delays in physical and mental development of children. Lead can have the largest effect on them, so that's why it's always in the news. And then it can also cause in adults kidney problems and high blood pressure. For copper, it causes stomach, liver, and kidney problems. So the rule was put into effect to minimize consumers' contact with those two minerals. The lead and copper rule is an action level. So an action level is different than a maximum contaminant level because In the distribution system, you only need to have 90% of the samples meet the regulation. So what happens is the customer samples are collected and they're listed from lowest to highest, and you go up 9/10 of the way on the list, and that's the number that's used to determine compliance with the action level. So you're allowed to have 10% of the samples in the system be over the action level for lead and copper and still be in compliance in the distribution system. The monitoring for the system is based on the size of the distribution system and then specifically on the high-risk sites. So if you have a lot of lead service lines or old copper pipe that has lead solder, those are the sites you're supposed to be toward. Originally, the frequency is every 6 months for initial monitoring. If you continue to meet the action levels, you eventually can go to monitoring once a year, and then you will go to half the number of samples that you have to pull. And then finally, if you continue to be in compliance, you go to once every 3 years at half the samples for the system. This rule is different than most samples because most samples are taken at the water plant for the water going out through the distribution system. Specifically for the lead and copper rule, this is a sampling of a first draw. This means the sample has to be 1 liter of water from a cold water tap that has not been used for at least 6 hours in the consumer's home. There is currently no upper limit on how long that sample can sit, so anything after 6 hours is valid, whether it be 12 hours, 24, 48, that technically with the regulation would still be a valid sample. The reason you want to take it on the cold water tap side of things is hot water can increase the rate of dissolution of metals, so that would increase the lead and copper numbers that the consumer would see. So they want you to focus on a cold water tap in the house. This could be from the bathroom sink or the kitchen sink where typically someone would drink. At the beginning of 2016, the US EPA put out a memorandum that made several recommendations for how you pull the samples for lead and copper. What they recommend now is no pre-flushing of the sample, which means you're not to inform the consumer at the beginning of taking the sample that they should pre-flush the night before letting the water sit for 6 hours. The idea of the pre-flush was to actually flush water through the sample lines in the house and allow the water to be relatively fresh at the minimum of 6 hours in the morning when the sample was pulled. Another thing they recommended was use wide mouth sample bottles so that when you take the sample in the consumer's home, you could have a higher flow rate. Basically open the faucet up to its full volume, and this would get you a better representative sample because any lead particulate would actually be flushed out of the sample tap into the bottle itself. Another thing they reiterated was that you are not allowed to remove the faucet aerators on the sink, which could trap particulate lead. You are to leave the faucet aerator on the sink if that's the normal operation for that kitchen sink or bathroom sink. So you collect your sample from the consumer home and you report your compliance. There are actions required if you have an exceedance, meaning you fail the lead and copper rule. The first part of that is distribution of public education. You need to notify your consumers that you had a violation of lead and copper rule and what that specifically means for them. One of the things that Flint, Michigan brought up at the beginning of this year was that they needed to make sure that you notify the public within a timely manner for what the results were for their system. After you violated the rule, you also have increased monitoring of consumer taps. If you were on reduced monitoring, which means samples every 3 years and half the number of samples, you now have to go back to the beginning and pull samples every 6 months and the full number of samples throughout the distribution system. In addition to that, you're required to develop and submit a corrosion control plan, which tells what you're going to do going forward to prevent another lead and copper exceedance. This could be adjusting pH, alkalinity, hardness, or adding a phosphate-based corrosion inhibitor to the system. Ultimately, they could also tell you to have actions required of a lead service line replacement out in the distribution system, and you should replace approximately 7% of your lead service lines per year. That's kind of a last course for the US EPA in the States, but it's one of the things that's come up recently is that maybe we should focus on doing lead service line replacement going forward. So if you have corrosion issues out in your distribution system, there's many issues and hallmarks that you could see out there in the distribution system to let you know these problems are going on. The first one is it's not very often that you get to go out to the distribution system and cut sections of the pipe like you see in the picture, but obviously you could have tuberculation and deposits on the inside of the pipe. In this case, in the cast iron pipe, that's calcium carbonate scale mixed in with iron to cause the rusty red tuberculation you see on the inside of the pipe. As that pipe becomes restricted and no longer a smooth surface, it costs you more to pump the same amount of water through that pipe in the distribution system because now the restriction is impacting your pumps. If those pipes get so bad that it influences the flow rate out in the distribution system, one of the things the fire department does is do flow rates on the fire hydrants. In those cases, that's actually setting the fire insurance rating for homeowners and the community itself. If they can't get sufficient flow velocity out of the hydrants, that increases the cost of insurance to homeowners in that municipality. As that scale and tuberculation builds in the system, it'll actually influence your chlorine demand in the distribution system. Chlorine will interact with that scale. You'll have a loss of disinfectant residual, and you'll have to feed more and more chlorine at the plant to maintain the same chlorine residual throughout the distribution system. If it gets really bad, you can have bacterial regrowth out in the distribution system. The bacteria, specifically iron, like to hide in that iron scale tuberculation and can cause red water episodes out in the distribution system. One of the first things you do when you have customer complaints is flush the water to flush the bad water out of the system. As scale and tuberculation builds up in the system, you can have to flush different parts of the system more and more times, and every gallon of water that you flush through the fire hydrant is a gallon of water that you've paid to treat at the water treatment plant but aren't recouping any costs as you flush it to waste to try to clear up the water quality issues in the system. Overall, flushing frequency can then lead to leaks in main breaks. As that pipe wall is impacted, the pipe can break and now you have a leak or main break and are losing water to the ground itself. Overall, all these issues above lead to a general decay of water quality in the distribution system, whereas the water leaving the plant may look crystal clear, may taste well, but by the time it gets to the consumer, it's picked up off flavors, off colors, and turbidity issues when it reaches the customer's home. All those things at the consumer's tap are going to lead to customer complaints, and they're going to either call you at the water plant or call someone at City Hall to complain about the source of their water and what's happening in it, and is it safe to drink. When we talk about corrosion-influencing factors in drinking water, we really talk about four things. There's the electrical component. You have different types of metals in the distribution system, whether it be cast iron, lead, or copper, and you have water, which all can conduct electrical current. You have the chemical makeup of the water itself. So these are the things you measure at the water plant on a daily basis. The pH, the alkalinity, the total dissolved solids. The chemistry of the water going out the door impacts how it affects the distribution piping. There's a physical component. So what is the makeup of your distribution system? Do you have a lot of lead service lines out there in use? Do you have a lot of older homes that have copper piping with lead solder? Do you have cast iron distribution mains? Do you have a lot of plastic PVC pipe in the distribution system? You know, what's the physical makeup of your distribution system? And then finally, there's a biological portion to the distribution system. The reason that you maintain a chlorine or chloramine residual out in the distribution system is you want to keep those bacteria in control and not growing in the distribution system. If iron bacteria or sulfur bacteria start to grow in the distribution system, those can lead you to red water complaints in the case of iron bacteria, or hydrogen sulfide rotten egg odor in the case of sulfur bacteria. So now the water has picked up either a color or an off taste in the distribution system. It's those four factors all together that influence what type of corrosion you could have going on out in the distribution system. Specifically, when we talk about chemical factors that influence corrosion, these are the main ones you typically look at. pH being the most common one. As we know, low pHs are acidic, and those would increase the corrosion rate on metals out in the distribution system. Typically, we think of higher pHs on the basic side of things as protecting the pipe by helping you to lay down a coating. Alkalinity is another thing that we look at. Alkalinity helps you form that calcium carbonate white coating in the distribution system. It also helps you control the pH by buffering the water so you don't see pH swings out in the distribution system as the water ages. You can have dissolved oxygen in the water, which increases the rate of corrosion. This will typically show up if you pull a sample of water at the consumer's tap and the water looks milky white for the first few minutes, but then as the bubbles dissipate, you no longer see the milky white, you have clear water. It's a hallmark that you have high dissolved oxygen in the water. How much chlorine residual are you feeding, or are you feeding a chloramine residual versus a chlorine residual? The higher you feed your chlorine residual, that increases the type of metallic corrosion that you have in the distribution system as the chlorine interacts with that scale. Chloramines actually act differently than chlorine, and a lot of research has shown over the years that as you change from chlorine to chloramines to meet other regulations in the drinking water, that it can impact your lead and copper numbers in the distribution system. Finally, DIC, or dissolved inorganic carbonate, is a measure of the conductivity of your water. What it's looking at is the higher your DIC, it actually interferes on the types of things you're doing for corrosion control. One of the new things in the US EPA document for optimal corrosion control that they look at is the DIC of your specific water, knowing that if the DIC is higher in one water over another, that you might have to do multiple things to make the water less corrosive. So you may look at pH adjustment, alkalinity adjustment, and adding a corrosion inhibitor in those waters with higher DIC in order to get corrosion protection for lead and copper in the distribution system. When we talk about methods to reduce corrosion in the distribution system, we really talk about a couple different methods that you can use. The primary one for a lot of water plants was pH adjustment. It was the simplest thing for them to add to the system, and they could raise the pH up to make the water less acidic to help prevent corrosion in the system. Two other things called passivation techniques were really carbonate adjustment or calcium adjustment. By adding lime or soda ash or different chemistries to the water, you could help form that calcium carbonate coating on the inside of the pipe to protect the bare metal. Corrosion inhibitors also fall into this category because they'll either be phosphate or silicate based, and they're relatively easy to add, and they can prevent corrosion of lead and copper, along with helping other issues out there in the distribution system. It's these top three on the list that are most commonly done to help with lead and copper and other issues with water quality in the distribution system. There are other methods to reduce corrosion. In your plant, you can have wholesale treatment changes where you reduce the DIC through either aeration, lime softening, or ion exchange. These would be wholesale changes to the water coming to the plant before you discharge it to the distribution system. Finally, one of the last things you can do is kind of physical protection, where you do cathodic protection of tanks or lines out in the distribution system. The way to think about this is you can't protect the whole distribution system, but there are certain critical parts of your distribution system, like the water tower or water tanks, that you want to protect. So you can either protect those with sacrificial anodes, or you could protect them by lining those tanks so that they don't corrode as quickly out in the distribution system. Specifically here in this presentation, we're going to talk and focus on phosphates in drinking water treatment. Phosphates have been used for a very long time in drinking water treatment. The first recognized use of phosphates in water treatment were all the way back in 1887. In the 1930s, specifically sodium hexametaphosphate was used for threshold treatment in potable water for control of calcium carbonate scale. Industrial plants would use this so that they didn't get the calcium carbonate scale impacting their boilers and water plants and having to shut down and acid clean that equipment. So they used sodium hexametaphosphate to keep that scale from forming inside those pieces of equipment. In the 1970s, zinc orthophosphates were introduced for the treatment of low hardness, very aggressive waters with low pH that were causing red water complaints out in the distribution system for customers. In the 1990s, with the advent of the lead and copper rule in 1991, it set limitations on the amount of permissible lead and copper in drinking water at the consumer tap, and phosphate use expanded in the U.S. When we talk about phosphate uses in drinking water treatment, we're really talking about two main applications. The first application being corrosion control, complying with the lead and copper rule, and then the other major use is sequestration, which is for color control, scale control out in the distribution system. In 2001, the last time a study was done by AWWA, it showed that 56% of all water utilities in the U.S. use some type of phosphate-based corrosion control and sequestration in the distribution system. At the time of this study, they showed that approximately $200 million were spent annually on phosphate products in drinking water. The results of that study also showed that it resulted in $4 billion in savings to those municipalities that were feeding a phosphate-based product, or what that means is a 20-fold return on investment. How AWWA came up with that number was every time that you flush water that you're not recouping the cost, there's a cost associated with that. Also, when you collect samples and have to pay for the testing to alleviate the concerns of consumers, there's a cost there. The replacement of infrastructure. If you can extend the life of that distribution piping and hold off replacing it for 10, 20 years, that's a huge cost savings of having to replace that distribution piping. It's one of the things in the last couple of years that AWWA has focused on, that the aging infrastructure, specifically on the water and wastewater side, is going to have to be replaced in the coming years, and there's a huge cost associated with replacing that distribution piping. The cost for phosphate products have a wide range depending on what your application is. Costs can range from as low as 30 cents a pound to $2 a pound, or really 1 cent to 10 cents per 1,000 gallons of water treated. And it's really depending on your application what type of phosphate product you would pick. One of the questions we get asked a lot at Carus is, we're adding a phosphate to drinking water, is it safe? Well, phosphates are something that we come into contact with on a daily basis. Phosphates are needed for us to survive. They're a food additive used in leavening agents in breads and donuts. They're a dairy emulsifier in cheese, and they're in the can of soda that you drink, a beverage, as 1% phosphoric acid. Typical levels in these kind of things that we eat on a daily basis could be as low as 10 to 50 parts per million to as high as 1,000 to 5,000 parts per million in one of these compounds. Compare this to the typical 1 to 2 milligrams per liter or parts per million we feed in drinking water. You can see we come in contact with phosphate at much higher levels in the things we eat. Phosphates are also used as pharmaceutical additives. On toothpaste, they're used as plaque inhibitors and whitening agents. They're also used in the manufacture of some drugs. But by far the largest use of phosphates in the industry is fertilizers on farm fields for growing stuff. Probably 90% of the market is applied to fertilizer to farm fields. One of the last places that we used to see a lot of phosphate products was cleaners and detergents. That's one of the products that phosphates have been removed for, because phosphate that's added as a cleaner and detergent would end up at the wastewater plant, and one of the things that wastewater plants are instructed to remove is phosphorus before they discharge to a river or stream. So in the case of cleaners and detergents, they remove those phosphate-based products from them to eliminate that source of phosphate at the wastewater plant. So the goal with a phosphate product is improving the finished water quality for the consumer. Obviously, there's a couple different things we're focused on here. You can focus on iron and manganese precipitation. If the water plant is not doing removal of those, then they would precipitate out in the distribution system. In the case of iron, cause red water. In the case of manganese, cause brown tea-colored water. If you have a high hardness water, you can have calcium carbonate scale control issues in the distribution system. In this case, you can see in the picture the distinctive pipe with all the white calcium carbonate scales, where you're actually impacting how much water you'd be able to get through the pipe as the pipe gets restricted over time. Finally, we are looking at pipe corrosion, the lead and copper in the consumer's home, and meeting those levels for the US EPA. Specifically, when we talk about corrosion control for lead and copper, what we're looking at is what I talked about earlier in the presentation, those US EPA action levels. For lead, 15 parts per billion, and for copper, 1.3 milligrams per liter. Typically, you think of phosphates used for corrosion control in very soft waters, less than 50 hardness, less than 20 alkalinity. In a lot of cases, that'll be surface water sources. But it can be in other types of water that are much harder. They can also have issues with lead and copper. For color control, preventing the iron and manganese from precipitating out, these are typically used when the iron and manganese are above the US EPA SMCLs. An SMCL is a secondary maximum contaminant level, which states that there's no health effects from drinking iron and manganese above these levels, but it's going to cause discoloration of the water and staining of laundry and fixtures in the consumer's home, which is going to lead to customer complaints. The SMCL for iron is 0.3 milligrams per liter, and for manganese is 0.05 milligrams per liter. Plants that are using oxidation always target to get well below those numbers in the distribution system. In most groundwater plants, if they don't have treatment in place with oxidation and filtration, they can use phosphates for sequestration to tie up the iron and manganese so they won't precipitate out in the distribution system. So they're used in place of oxidation in groundwater. Calcium carbonate scale control, like I talked about that picture earlier, the higher the hardness of the water, the higher your pH, you have a tendency for calcium carbonate scale to precipitate out of solution. As you get above 150 milligrams per liter as calcium carbonate up into the 200, 300, and 400 milligram per liter range, calcium carbonate scale will tend to build on itself and start restricting the pipe. This can also impact water meters as it plugs up the small parts in the water meter and you don't get accurate readings on what's being used water-wise in the distribution system. The phosphate will sequester the calcium carbonate and prevent it from precipitating out of solution so you don't restrict those pipes and water meters in the distribution system. So when we talk about phosphates and their two different uses, there's two very distinct classes of phosphates. There's an orthophosphate, which contains one PO4 unit by itself, and there's what's called condensed or polyphosphate, which contains several PO4 units chained together. In the case of orthophosphate, the simplest phosphate molecule out there, it's one PO4 unit by itself. Polyphosphate, which contains two or more PO4 units linked in a chain, will be used for sequestration. And then as I talked about earlier in the presentation, sodium hexametaphosphate is three or more PO4 units in a ring structure versus a straight line chain. We'll talk more about what ortho and polyphosphates do in the next couple slides in the presentation. Specifically, corrosion control mechanism is that we know phosphates form films over pipes or metals out there in the distribution system. Specifically, phosphates are anodic film formers in the distribution system. They're also acting as a cathodic inhibitor in addition to the anodic film former, providing a barrier between the metal surface and the oxygen in the water itself. The research has shown that there's a very microscopic thin film that forms on the inside of the pipe, and these very insoluble compounds, phosphate salts, form on the surface. Even today, we're still doing research at AWWA and other national organizations to see how these products work in the distribution system based on the varying water quality we have across the U.S. But knowing that we form this film that prevents metals from dissolving from the pipe surface into the water. Specifically, if you go to the AWWA national website or many other national websites looking at corrosion control, you can find a lot of articles on orthophosphate research. The articles will detail how the phosphate precipitates with the 2+ valence metals in the system, so they combine with the calcium and magnesium that form the total hardness in the system, and how they also bond with the iron pipe, the lead and copper pipe in the distribution system to form that thin film. Michael Schock has done a lot of research showing that formation of insoluble film with the phosphate products out in the distribution system. Some of the research shows that as little as half a part to 1 milligram per liter as orthophosphate reduces the amount of iron that would release from a cast iron pipe by 2/3. But overall, the whole body of research for orthophosphate shows that they reduce the amount of corrosion issues that you have in the distribution system. So they'll eliminate a lot of lead and copper issues and help with iron issues in the distribution system. Specifically, one of the orthophosphate products that's used is a zinc orthophosphate, commonly referred to as ZOPs. They're a combination of orthophosphate and a zinc salt, and they're used for corrosion control only because they do not contain any polyphosphate, which would be used for sequestering of metals. The reason zinc orthophosphates were used was they were very quick to form a film on the inside of the pipe. That's a piece of copper pipe with a zinc orthophosphate film forming on the picture that you see. Passivation would take place in weeks, so you would feed the zinc orthophosphate at the water plant and that film would form very quickly out in the distribution system. The dosage for a zinc orthophosphate would typically be 1/10 of a part to 1/4 part to as high as 1/2 a part as zinc out in the distribution system, and then anywhere from 1/2 a part to 2 milligrams per liter as orthophosphate in the distribution system. Once you started feeding the zinc orthophosphate, you would see that level of zinc and orthophosphate come out throughout the distribution system as that coating forms. One of the issues with zinc orthophosphates is the wastewater plant in the municipality has a zinc loading limit on their discharge and on their sludge from the wastewater plant. So if you're feeding a zinc orthophosphate, one of the concerns is on the wastewater side that zinc as it impacts the wastewater plant. One of the things that's happened in the recent years is some plants have switched away from zinc orthophosphates to straight orthophosphate or blended phosphates because of this zinc issue at the wastewater plant. When we talk about an optimal orthophosphate dose, typically you're going to be at a minimum of 0.5 milligram per liter as orthophosphate. And that's going to help you reduce lead and copper solubility in the pH range of 7 to 9. The US EPA documents talk about feeding up to 3 milligrams per liter as orthophosphate in the distribution system, and that as you increase that dosage from 0.5 part to 3, you'll continue to see reductions in lead and copper solubility out in the distribution system. Most systems, depending on water quality, can have a maintenance level of around 1 milligram per liter as orthophosphate in the distribution system. Things that would cause the dosage to be higher toward 2 and 3 milligrams per liter, as you tend to have lower pHs and lower hardness in the water, you need more of the phosphate to help form that coating in the distribution system, and so you'd increase your dosage from 1 milligram per liter up to 2 or 3 milligrams per liter based on that water quality in the distribution system and have the higher dosages. So the first case study we have here is on Carus 4100, and the background of this plant was they were using pH adjustment for corrosion control at this plant. And what they were using was two products. They were using soda ash and they were combining it with calcium chloride. What they were getting was they were getting consumer complaints in the distribution system from a bad metallic taste to the water caused by the addition of the calcium chloride and the soda ash. They were still getting some periodic dirty water, red water complaints from iron corrosion in the system, and they were still having issues with the lead and copper levels being above the action levels, so they wanted to reduce those numbers as well. The plant operation, it was a groundwater filtration plant, 1.5 MGD, and their water quality shows that there wasn't really any iron in the water leaving the plant at 0.04 milligrams per liter, so that would tell you the red water complaints were coming from corrosion in the distribution system because there wasn't iron in the source water. Manganese was 0.01 milligrams per liter, so below the 0.05 secondary maximum contaminant level. The pH they were adjusting to was 8.4. Their hardness in this water was only 24 milligrams per liter, so very low on the hardness scale. Alkalinity down at 68 milligrams per liter. So what they chose for their treatment was they were going to go to 100% orthophosphate product, and they chose a dosage starting of 1 milligram per liter as orthophosphate in the distribution system. The feed rate for that product was 23 pounds of product per million gallons treated. When they made this change, they also looked at doing two other treatment process changes in the plant itself. So they reduced the pH from 8.4 down to 7.5, reducing the amount of soda ash that they were feeding to the water, and that saved them 37% in operating costs. They decided that since they were adding the orthophosphate, they no longer needed the calcium chloride to add calcium to the water, so they completely stopped feeding calcium chloride, and that saved them 50% in operating costs. Combined in the reduction of the two chemicals that they were feeding prior to the phosphate addition, they were able to pay 87% of the cost of the phosphate product in reductions in the two other chemicals. What did this lead to? They had improved taste. They weren't getting customer complaints for metallic tasting water out in the distribution system with the addition of the orthophosphate. They eliminated their red water complaints that they had in the distribution system. Their lead levels dropped to less than 2 parts per billion, so well below the 15 parts per billion of the action level. And the copper levels dropped to 0.05 milligrams per liter after 2 years. So the treatment change worked across the board, providing better water quality to the consumer in the distribution system. Sequestering mechanisms. So these are the bonding of a polyphosphate or a condensed phosphate to the metals that are in the water. The idea here is you prevent the chlorine that you feed for disinfection from oxidizing the metal that's in the water to begin with. Typically what you're focused on is iron and manganese. The result with sequestering is if you had iron, the prior water would be rusty orange once you add chlorine. If it's manganese, the prior water would be brown at low levels or black at higher levels in the distribution system. The other application would be threshold treatment for calcium carbonate scale control. The idea here is you keep the calcium bicarbonate ion pairs from clustering to where they'd actually form a crystal and plate out and cause that distinctive white scaling you would see on the distribution system. The idea here is just enough phosphate to inhibit the crystal growth so you don't get the scaling issues you would see with calcium carbonate. Same thing here as with orthophosphate. There's been a lot of research done over the years for polyphosphate. You can go to the AWA website, the EPA website, and look up articles. Sequestering of the metals depends on what the water chemistry is. So how much iron and manganese do you have? What's your pH? What's your alkalinity in your water? The research also shows that as you apply a polyphosphate to the water, it reduces the apparent color and turbidity, specifically for iron and manganese out there in the distribution system. Polyphosphates have been shown to improve disinfection in the distribution system. One of the things polyphosphates will do is they'll sequester metals from that tuberculation and scale in the distribution system, and that allows your chlorine to more effectively attack the biofilms out in the distribution system. One thing that all polyphosphates do over time is they're going to revert from polyphosphate to orthophosphate over time. So one of the things to keep in mind if you're feeding a polyphosphate or a blended phosphate product that includes poly is that they do have a shelf life of 6 months to 1 year because that polyphosphate is slowly going to revert to ortho over time. So when we think of polyphosphates out there in the distribution system, what we're really looking at is trying to control color issues in the distribution system. In this case, they're out there flushing a fire hydrant because they had red water complaints in the distribution system. In this picture, you can see they've got the fire hydrant open, flushing to the ground. There are two things I always like to point out in this picture that nowadays you wouldn't do. You would not use a pipe wrench to open a hydrant because you chew up the top of the hydrant nut, so you'd be using a hydrant wrench. And then in most municipalities and states, you're required to have a diffuser on the discharge from the hydrant and dechlorination before you discharge the water to the road. One of the things you can keep track of if you have colored water issues in the system is how long does it take when you flush a hydrant for the water to flush from red, brown to clear. The faster that water clears up, the cleaner your water is and the less tuberculation and scale you have in the distribution system. Ideally, when you flush a fire hydrant, it flushes dirty for a few seconds, and that's mainly because of the water trapped between the distribution main and the fire hydrant itself. So you will always see at least a little bit of dirty water when you first open a hydrant. As the water switches to water that's in the distribution main, it should clear up relatively quickly unless you have a lot of scale and tuberculation. In this case, you can see the water is flushing clear relatively quickly in this hydrant. One of the things you can keep track of when you do corrosion control issues and polyphosphate in the distribution system is how fast does it take to the water to clear up. The faster the water clears up, the better you have that corrosion and color issues under control in the distribution system. One of the things, depending on where you're at in the U.S., is how much calcium carbonate do you have in your water as total hardness. The map here is from the USGS, showing you a map of the U.S. and surface water sources. And you can see, depending on what coast you're on, you can have very soft waters of 0 to 60 milligrams per liter, to where here in the Midwest and out west before you get to the coast, you can have hardnesses of 180 to 250 to 300 milligrams per liter. One thing this map doesn't show is that groundwater can vary greatly from site to site throughout the U.S. Depending on what type of well you have and how deep the aquifer will determine how much hardness you have to sequester in those wells. In the earlier case study for Carus 4100, that was at a shallow well in Florida that did not have much calcium carbonate influence, so it had a very low hardness. In the Midwest and other parts of the U.S., you can dig a well and have 300, 400, or 500 hardness in the water, depending on that aquifer. So that'll determine how much scaling issues you could have in the distribution system. One of the things I like to show is a schematic of biofilm removal. It comes up often that when you feed a phosphate product, what influence does it have out there in the distribution system? In this case, you can see the metal pipe surface out in the distribution system, and you can see the biofilm that can grow on the inside of the pipe and the different metals that will be trapped inside the pipe. What will happen is, as the polyphosphate is being fed to the distribution system, it'll actually go out with that biofilm and interact with that scale and actually slowly remove the metals in the biofilm itself. As the polyphosphate removes those metals from the biofilm, it punctures little holes in the biofilm, allowing your chlorine or chloramine residual to get deeper and deeper penetration into the biofilm. What this shows is that over time, as you remove those metals from the biofilm and you maintain your chlorine and chloramine residual, you're able to clean up that biofilm and remove it from the distribution system and prevent any issues that that biofilm causes in the distribution system. It's one of the reasons why polyphosphates are fed in the distribution system, because you can help clean up that biofilm and scaling you have in the distribution system over time. When we talk about polyphosphate dosing, the dosage can have a quite large range, anywhere from a half a part to 4 milligrams per liter as total phosphate. The dose for your product is really going to depend on what you have to sequester in the water. If you have a lot of iron and manganese in the groundwater sequester, you'll be on the higher side of that dosage. If you have lower levels, your dosage will be on the lower level. One thing that some municipalities will do is when they do flushing in the distribution system, they'll increase their phosphate dosage to the distribution system to help break up any scalar tuberculation that's formed over the course of the year and allow that to be flushed out of the system by breaking up that scale. So we've talked about polyphosphates for sequestering and orthophosphates for corrosion control. So in 1990, when the lead and copper rule was promulgated, a lot of systems looked at that they had two issues they needed to comply with. They need both corrosion control and sequestration out in the distribution system. So poly-ortho blended phosphates started to be fed to distribution systems throughout the U.S. What they do is they provide moderate corrosion control, so some lead and copper control to the distribution system. They help you prevent and remove scale deposits of iron, manganese, and calcium carbonate in the distribution system. And because they impact the biofilms, they can help improve disinfection, because as you remove that biofilm from the distribution system, you don't need to feed as large a chlorine dosage to maintain the same chlorine residual throughout the distribution system. So the idea here, feeding one blended product to get you all these benefits to the drinking water. So optimal poly-ortho blended phosphate dosing. The dosage can have a range here as well, from as little as 0.2 to 1.5 milligrams per liter as orthophosphate, and then a total phosphate dosage of a half a part to 4 milligrams per liter. The difference between the ortho and the total number is how much polyphosphate you would have in the system. You can't measure polyphosphate directly, but by measuring the total phosphate and the ortho, you can get at it as the difference between those two. The dose of the product that you're feeding is going to be dependent on the water quality and the type of blended phosphate product that you're feeding. Your objective is typically going to determine how much you're dosing. If you're only targeting really corrosion control in the distribution system, you'll be on the lower end of that dosage side. If you're looking at sequestration of metals in addition to corrosion control, then you'll typically have one of those higher dosages listed. Case study, this one is for Carus 8500. The background for this plant was to reduce the lead below the action level. They were currently violating the action level at 22 parts per billion, with the action level being 15. They wanted to reduce discoloration in households they were having standing on fixtures and laundry in homes, and they wanted to reduce the long hydrant flushing times. When they were going out to flush hydrants in the distribution system, it would take them greater than 30 minutes of flushing water before the water in the hydrant would clear up to clear. They were a groundwater filtration plant, and they had 3 groundwater wells that they were going to treat. These plants were interesting because they had radium removal with HMO, or hydrous manganese oxides, for radium removal in the plants. The plant was 1.1 MGD from these 3 wells, and they served 7,500 customers. When you looked at their water quality, the pH was 7.3 to 7.5 in the wells, iron of 0.1 to 0.5 milligrams per liter, which could be some of the cause of the red water issues in the distribution system because you're above the 0.3 milligrams per liter for iron. Hardness was 280 to 340 milligrams per liter, and the manganese was low at 0.01 to 0.05 milligrams per liter. So the product they picked for this water quality was a blended phosphate, and they picked a 50-50 blend of poly to ortho. Their dosage for the system was 1.5 milligrams per liter as total phosphate, so that would give them 0.75 as ortho and 0.75 as poly, and that feed rate translated to 35 pounds of the product per million gallons treated. Within 90 days of applying the blended phosphate to the distribution system, they had lead levels drop from 22 parts per billion down to 7.5 parts per billion. So now you're less than half of the action level of 15 parts per billion. Hydrant flushing times were reduced from 30 minutes to less than 5 minutes. So this reduced the amount of operator time in the distribution system to flush those pipes, plus the amount of wasted water. And then the customer complaints for red water in the system got reduced from several a month to almost none. So across the board, the blended phosphate helped them meet all their treatment goals that they had in the system. Another case study, this case for Aqua blended phosphate. The background of this plant was that they had heavy tuberculation in the system. They had reduced flows that impacted hydrant testing. They had periodic dirty water, red water complaints, and they had 90th percentile copper levels at 2.25 milligrams per liter, which was above the 1.3 milligram per liter action level. The treatment plant was iron removal with aeration and then gravity filtration, and they treated 2.5 mgd. If you look at their water quality, they only had about 0.1 to 0.3 milligrams per liter of iron going out the door, so just barely below the secondary maximum contaminant level, which leads you to tell that the corrosion and the red water issues were coming from corrosion of the distribution piping. Manganese was 0.01 milligrams per liter. The pH fell in the range of 7.6 to 7.9, and the hardness was 180 milligrams per liter. So they chose, based on this water quality, they were going to feed a blended phosphate and a ratio of 70 poly to 30 ortho, and their dosage was going to be 1.5 milligrams per liter as total phosphate. And this led to a feed rate of 38 pounds per million gallons treated. One of the things they looked at, because hydrant testing showed flow issues in the distribution system, is they looked at the flow improvement from those hydrants after the application of the Aqua phosphate. Depending on the hydrant they were testing, they saw anywhere from a 10% to a 40% increase in hydrant flow rates through those hydrants after applying the Aqua phosphate. They had reduced red water complaints in the distribution system as they were preventing those corrosion products from forming in the distribution system, and their copper levels decreased 65% all the way down to 0.79 milligrams per liter, so they were below the 1.3 milligrams per liter of the action level. So one of the things that you need to keep in mind when you're picking a phosphate product is which phosphate to use. The choice can be as critical as the dosing. So what you really want to look at is two different factors. What is the water quality that's leaving the plant, and what is the water quality in the distribution system, and does it change? So is the water quality of the plant perfectly fine, but when it gets out to the distribution system, are you picking up other issues in the distribution system? Specifically, what types of problems are you having? What are customers calling you to complain about in the distribution system? Are they complaining about red water issues? Are they complaining about taste issues in the distribution system? If so, what type of taste issues are they complaining about? Basically, do some research when you're talking to these customers to find out what kind of issues you have in the distribution system. What are your treatment goals? So if you're going to add a product to the distribution system for phosphate, are your goals mainly corrosion control? Are they mainly sequestration? Are they a combination of the two? That'll help lead you toward the product that you would pick. Things that we look at Carus when we're selecting a product and the dose that we're going to do. What we would like to determine is the hardness of the water in the distribution system. How much iron and manganese do you have after filtration or oxidation and filtration if you have it, keeping in mind that if you're above the secondary maximum contaminant levels for iron and manganese, that you'll need to do sequestration to prevent those things from precipitating out in water. We want to look at the orthophosphate if you're a groundwater plant, because you're going to have typically some background orthophosphate, and when we pick a product in a dose, you're going to take what your background orthophosphate is and add it to the selected dosage that's picked, and know that you need that combination. So if you had a background ortho of a half a part in some wells, and your target dosage is 1, you really need to see 1.5 in the distribution system to be at your target level of 1, because you have that half a part in the background. And then finally, what's the pH of your water out there in the distribution system? With a blended phosphate, you can be between pH 6 and 9. Ideally, we'd like you to be between 7 and 8 to be optimal. And specifically, if you use a zinc orthophosphate, you really want to be between pH 7.3 and 7.8 to make that the optimal process. Or on the far side, 6.7 and 8.2 with those products. Typically, we'll look at the water quality at the plant and then out in the distribution system when we make a product selection and a dose. Specifically, when we're looking at a water quality, if you have a low hardness, which would be a corrosive water, low alkalinity, and a low pH, and no iron and manganese sequester, we would be looking at products in the Carus 3000 and 4000 series, which would be zinc orthophosphates and orthophosphate-based products. If you have a very high hardness, a high alkalinity, you have a high iron and manganese content, then we would be looking at a straight polyphosphate product in the Carus 1000 series. For most water qualities, we would be looking at some type of blended phosphate with both corrosion control and sequestration abilities, and this would fall into our Aqua series or our Carus 8000 series of products. As you can see, there's some overlap, so there's places where you could choose different types of products and different dosages and still achieve your treatment goals. So you can choose different products depending on what you're really focused on. Phosphate injection applications, one of the easiest things to apply is phosphate. So you want to inject your phosphate solution using a corporation stop in the main prior to chlorination, specifically if you're looking at sequestration. So in the case of groundwater, you're always going to want to apply the polyphosphate or the blended phosphate prior to your chlorination because chlorination is going to be your oxidation. So it would drop the iron and manganese out of solution. In a surface water plant, you're obviously going to do, in most cases, oxidation, coagulation, filtration. The phosphate's going to be added at the back of the plant, usually after filtration as one of your final chemicals to the treatment process. Phosphates can be fed neat directly out of the container or the bulk tank. You could use carry water if you need to, and you could have a static mixer in the line, but phosphates blend in with the water very rapidly. Typically, phosphates are fed with a peristaltic or a membrane chemical feed pump. Ideally, you'd love to have the pump flow-paced and SCADA controlled so that you can make adjustments to it remotely. In the case of groundwaters, a lot of times pumps are tied into the power for the well pump, and the pump kicks on when the well kicks on, and so you're only applying phosphate when the well is pumping. Like I said earlier, you want to keep in mind that you inject first if you're sequestering, so the phosphate needs to go prior to your chlorination. Typical things that we would like to see a customer to measure on a daily basis, and most states would require a plant to do these. We would love to see a calibration of the metering pump in mils per minute or gallons per hour, or if the tank's on a weigh scale, how many pounds of product you used per day, or have a level indicator on the day tank and the bulk tank for how many gallons were used per day. All this information is critical because you can take that information to see how much phosphate you're applying to the drinking water and what should be the associated dose of phosphate that you can measure in the distribution system and make sure that those numbers add up and make sense for the system. In this case, you can see a small mini bulk system with 2 tanks and a mixer where they're mixing dry phosphate into solution, and then the metering pump mounted to the wall, applying it to the water itself. In addition to measuring the levels of phosphate that you're feeding out of your tanks, there's also ways to measure the phosphate out in the distribution system. We typically at Carus use the US EPA approved absorbic acid method 8048, and it measures orthophosphate residual in milligrams per liter. It's a very easy test. You add the powder pillow, you wait for 2 minutes, and the sample turns light blue. After the sample turns light blue, the darker and darker the color becomes, is the higher and higher the level of orthophosphate that you have in the system. This test is relatively easy to run, and you can run it when you collect free chlorine samples out in the distribution system or chloramines. Just collect more sample and then run this as a separate test so that you have a data on what the orthophosphate levels are out in the distribution system. Typically what we would say for a customer that's feeding a phosphate product, we'd ideally always love to see orthophosphate tests at the finished water tap at the treatment plant itself. We'd love to see some samples out in the distribution system at multiple points so you have an idea of what the orthophosphate level is in the distribution system. And then we want to focus on places where you have issues or dead-end lines where you might see a drop-off in residual or chlorine or other water quality parameters and see what the levels of orthophosphates are at that level. Once you've started feeding a phosphate product and have formed a film in the distribution system, that orthophosphate level throughout those distribution points at 1, 2, and 3 on the picture should all be relatively similar levels. So if your target's 1 milligram per liter after 90 days or 6 months of feeding, you should see about 1 milligram per liter at all 3 points in the distribution system, letting you know that you're forming a coating and have maintained control out in the distribution system. There's some other things you can look at if you're picking a phosphate product for the first time or you want to monitor what your current program is versus a new treatment change. You can do coupon-based monitoring. This is the NACE protocol, National Association of Corrosion Engineers, and what you're looking at is putting test coupons out in the system and looking for how much of that coupon erodes over the course of a year in the case of mils penetration per year, or MPY. Typically what you're going to look at is a test duration of 30, 60, or 90 days, with 90 days being most common, because in the first 30 days these new pieces of metal corrode faster than they would do over the long term, and so your numbers have much more bounce in the shorter coupon tests. What you're also going to want is a coupon rack on non-treated and then treated and distribution loops. At the minimum, you'll want 2 loops, one prior to your phosphate addition and then one after your phosphate addition, to see what that treatment change is having to your coupon data. And what you want to focus on is the trend of the data. So as you make treatment changes or you change your phosphate product, is the data getting better? Are you getting better corrosion rates with your new treatment change? Specifically, here's a picture of a coupon rack. The typical rack that you would see in the distribution system would be a 3-position rack, and you would have copper, lead, and mild steel coupons that you would put out there in the distribution system. The rack is controlled with the silver dole valve that impacts how much water would flow through the rack. Typically, you're going to control it at 1 gallon per minute or 2 gallons per minute going through the coupon rack in the distribution system. And like I said earlier, you'd have 2 of these, one on treated and one on non-treated water. When we look at the coupons, you're obviously going to get some numerical data, but you can also physically look at the coupons when you put them in and pull them out. In this case, this was a coupon exposed to Florida surface water for 90 days, and this was the mild steel coupon, and you can see the rust and scale that had formed on the coupon itself with no phosphate treatment. The coupon to the right was treated with 50-50 poly-ortho blend, and you can see that you can actually see the coupon, you can actually read the coupon number on it, and you have a little bit of formation of rust on the sides of the coupon, but physically you can see that the treatment change made a very drastic difference to the water quality. And that's one of the things you can do with coupons, is make a treatment change and then see both physically and then in the numbers, did you make a change for the better for corrosion control in your distribution system. One of the last things I like to touch on during any presentation is the personal protective equipment for the operators handling these products. Specifically, if you're using PPE for phosphoric acid or zinc orthophosphates, the pH of these products is typically less than 1, and they're considered corrosive inorganic liquids. So the PPE that an operator should be using when he handles these products is goggles and or a face shield, a rubber or appropriate polymer gloves, a rubber apron. If you're taking a bulk delivery, then you may even want to upgrade all the way to a complete acid-resistant suit and rubber boots. Basically, the amount of exposure that you could have to these products, since they're corrosive acids, you want to be geared up depending on what could happen. These products, both phosphoric acid and zinc orthophosphates, are considered DOT hazardous for shipping, so the truck has to be placarded and all the right labels attached to it. One of the reasons that blended phosphates are picked is the PPE requirements go down, or you can also see some pH-adjusted orthophosphates like monosodium orthophosphate used. The reason for these products being picked is because safety goes down immensely. The pH for these products is typically neutral, somewhere between 5 to 8 or 9, depending on the product type you're using. And the PPE goes down to safety glasses or goggles if you think you have a splash hazard with the product, and then rubber or appropriate polymer gloves if you think you're going to get in contact with the product. These products also are no longer DOT hazardous for shipping, so if a water plant had multiple well sites, they could actually have the product delivered to one site and then move the product themselves from site to site, since the product is no longer DOT hazardous for shipping. To sum up here, so summary of phosphate use in the U.S. is pretty extensive. Very small systems, groundwater systems, 1 MGD or less can use phosphate products, to very large systems. Large systems can include the city of Chicago, New York, Miami, Los Angeles, that all feed phosphate products to the distribution systems. The idea of a phosphate product being added is the benefits for the products are worth the cost of the product that you're adding. Ideally, you'll be feeding them to reduce lead and copper to meet that lead and copper regulation. If you're using them for sequestration, you have clearer water without solids out in the distribution system. You could reduce your flushing times. You can reduce your disinfection demand. Basically, the benefits of phosphates are overall better water quality out there in the distribution system for your customers.
Great. Thank you, Darren. That was a great presentation. And here we have a quick look at our regional sales managers. They are based by territory, so you'll see the territories, their names, and their phone numbers. If you would like emails or additional contact information for any of your regional sales managers, please let me know and I will be happy to get that information to you. And here is Darren's contact information as well. And at this time, I would just like to remind you that we will send out the recording link of this presentation today to all attendees. If you're interested in the PDF of today's presentation, let me know, or if you have any additional questions, please contact me. I can get you in touch with Darren or your regional sales manager. And if you have any questions, go ahead and type those into the question pane in the GoToWebinar section. And it looks like we have a question coming in. You mentioned feeding PO4 prior to chlorination for sequestration. Could you elaborate further?
Yeah, so specifically in the case of sequestration, you want to be prior to chlorination because chlorination is going to act as your oxidizer for iron and manganese in solution. So you need to sequester the iron and manganese prior to the chlorine being added so that you can keep them in suspension. Typically, we kind of use a rule of thumb in the case of polyphosphates or blended phosphates for sequestering that we would ideally love for you to have a static mixture between the phosphate application point and the chlorination point, but that's not always possible. So we use a general rule of thumb of for every 1 inch diameter of the pipe that you're injecting into, that you would love to have about 1 foot of distance between the phosphate and the chlorination. So if you had a 6-inch pipe, you'd love to have 6 feet between the 2 application points with the phosphate being first so you can tie up the mineral content. One of the things that can shorten that distance, if you have a bend or an elbow in a pipe, especially in a groundwater plant, there usually are some bends and elbows in the pipe, put the phosphate on one side of the bend or elbow and then put the chlorination on the other side, and you'll get the mixing of the phosphate into the water itself for sequestration. If you add the phosphate after the chlorination, what's going to happen is any metals that have precipitated out with the chlorination, you're not going to put them back into solution once they've precipitated out. So if you had iron and you chlorinated heavily, you get a lot of red water. Adding the polyphosphate is not going to make that color go away. It's going to be there, and you're going to have to remove it with filtration because you've already oxidized the iron to a solid.
Great. Can you briefly discuss the different packages available for the phosphate products?
So phosphate products are available in a lot of different package sizes. We have as small as 5-gallon containers for some products to 55-gallon drums to 250-gallon totes to bulk 4,000-gallon shipments. It's really going to depend on your application and how much product you're going to use, which package size you want to pick. Typically when we work with customers, we're going to look at their water quality, establish a dosage, and then determine how much product they're going to feed. And then if they're using the product for sequestration, what we want to do is try to minimize the amount of time that product sits. Because polyphosphates revert to ortho over time, you'll lose some sequestering ability. So what you don't want to do is have a customer take bulk and then hold on to it for 2 years and use it over the course of 2 years because you're going to lose some of your sequestering ability over time. Ideally, what we want to do with a bulk customer is we want them to be using, if it's a polyphosphate-based product, we want them to be turning it over every 6 months. In the case of a product like a zinc orthophosphate or an orthophosphate, typically there you don't have to worry because the ortho doesn't revert to anything. We'd ideally like you to switch over once a year just so you're moving product through your system and through your tanks and through your lines. So really we're going to look at how much you're going to feed, and that determines the package size.
Great. Another question came in, where can the literature be obtained for the Aquamag and other blended phosphates? I will go ahead and answer that one. We do have a phosphates information on our Carus Corporation website, so www.caruscorporation.com. If you find any questions when you're going through any of that literature, please get in contact with your regional sales manager. They can definitely walk you through, especially any of the technical aspects of those documents. Or if there are any questions that you have that aren't necessarily answered on the documents on the website, let me know and we can get you additional information. Okay, how do we know the phosphate product is what we ordered when it shows up on site?
So 2 things. There should be shipping papers with the phosphate that's shipped to you. Typically, you'll either have a certificate of analysis or a certificate of compliance saying that the product meets a certain specification. You can also do some testing yourselves. This comes up over the years, and we can establish and tell you what the specs of the product are. Usually a lot of bid documents will lay out what the product is supposed to be. Kind of the two easiest things you can test is pH and specific gravity, which will tell you if the product has the right pH based on the products that are in it and the right specific gravity, meaning it's heavy enough to contain those phosphate products. We have some customers will actually then go a step further and actually do an ortho test or a total phosphate test on the product itself, so then you can measure that as well. And basically with those three pieces of data, then you know what the product is that you're getting meets the spec that you have for it. But typically the pH and specific gravity are the ones that are done quickly, and then you have to do some dilutions or some digestions to do the total and the ortho to get those numbers. But those are things we would suggest to customers to look to make sure they're getting what they think they're getting.
And as you mentioned, with that certificate of analysis, our quality control department analyzes each lot of our phosphates. So those are all individually tested and documented on those C of A's. And then it looks like one more question. Are pipe loop studies recommended as well as coupons?
So with the Flint, Michigan issue at the beginning of the year, you're seeing a push toward, rather than just using coupons, also doing pipe loop studies. The data can be a little bit similar between the two. The benefit with a pipe loop study is now you can actually let the water stagnate and do first draw samples. So whereas with the corrosion coupon loop, you're really looking at just the corrosion rate in kind of a gross manner that's flowing through the pipe over time. With the pipe loop study, now you can actually try to mimic the plumbing in the consumer's home and see what those first draw samples would look like by letting the water sit in those lead pipes. Pipe loops are much more complicated, much more harder to put together and do, but you can get better data from those systems. We typically like coupon studies, or actually the best thing is actually the real world data in the distribution system. With Flint, Michigan, that makes some people nervous because obviously if you make a mistake and have bad water quality out there in the distribution system, you can be in the news. So one of the things we like to look at is now the coupon studies in addition to the real world data. But yeah, pipe loops will give you more data if that's what you want to run. So.
Great. That looks like all the questions for now. If you think of any after we conclude here, please again reach out to us and we'll get you those answers. And as I mentioned, this concludes our 2016 webinar series, so be on the lookout for our 2017 webinar series that we should be announcing soon. We thank Darren again for his presentation today and thank everyone for attending and joining us today.